Energy System Modeling, Exercise 6. So you can go ahead and download the exercises again from the Moodle folder. And this is what you're going to get. You have some files already in here, but let's start looking about the assignments. So we are using this ERA 5 data from Copernicus. So this is the climate data that you can find via this link. You have to register to this website and log in to download this. So what I did, I downloaded from here this wind, and there's this 100-meter U component, 100-meter V component, and U and V component just mean that they are east-west and north-south direction components, so you can actually get the direction of the wind as well as the average velocity or the mean velocity. And then let's take the 10-meter components of the wind from here. Then you can select the year 2024. That's what I used. And all months, all dates, and all times. Geographical area means that how you are going to limit location. So what kind of a grid size are you going to download? So what I had in here was 70, 19, 32, and 59, which corresponds to pretty much Finland outside borders. And then you can use this net CDF4. And then you make an API request. I'm not going to do it at the moment since I already have those files, but it's going to take time for you to download them. So my requests in here, you can see, well, this went through really fast yesterday. So you can see the details from here. I downloaded all of these. But for Moodle, these files were a bit too large, so I downloaded those individually. So each of these components that I have in here, I downloaded separately, and I have it in this Moodle folder, as you can see in here. So these are downloaded from this ERA data. So they are this .nc format, and how we can open that, we can use Python for that. So let's go ahead and prompt a program with a ChatGPT. So I have ERA 5 data for different files. So I'm going to take the file names from the folder. Let's see here. So let's take this one. And the other one was V component. And then I can copy and paste these and add a 0. Give me a code in Python that calculates the wind velocity separately at 10 and 100 meters in Tampere. So the assignment was to extract the data from Tampere. And by the way, the coordinates can be found in here as well. So in Tampere, plot the results and write them to Excel Tampere speed XLSX. Let's see. So in some cases, there's going to be some trouble with the names of the files. And for example, I got troubles with the timestamp. But if you get an error, then you just put it back in here and see how the code corrects itself, or the AI corrects the code. And in here you can see actually there's the component u to the power of 2 and v to the power of 2. So, and you're going to take a square root out of that. So that is the way to calculate the velocity in there. So let's see if we can extract those. I'm going to try and, so you have a ready code in here, this Copernicus Tampere, but I'm going to try if we can live prompt this. So let's see. You're going to see if there's going to be some errors. Yeah. So as I said, there was some trouble with the time. So let's go ahead and put this back in the AI and see if it can correct it. So give me the entire code. So hopefully it's gonna start editing it now. So we'll hope that that fixes the time problem from here. And again, remember, if you're missing some of these libraries, you can download them from the settings project Python interpreter and from this plus. Or you can use the command prompt to install them. So you write CMD here, command prompt, and you can install those packages from here as well. You can ask ChatGPT for the command. So let's see if we can get this one to work. Hopefully so. Seems to be doing something. Yeah. So what we have in here is the 10-meter wind speed and 100-meter wind speed. So it seems reasonable in a way that 10-meter wind speed is slower and the 100-meter is more is higher. So let's see if it made the folder for or the file for us in Excel. So we can go ahead and open that. Yeah. So Tampere region is in here. And the first thing we can do is we can start comparing it. So there are alternative data sources as well. So we're going to go to Finnish Meteorological Institute and let's get wind speed hourly. We're going to get 2024 January 1st and then 2025 January 1st UTC time. We're going to see from the map if we can find Siilinkari, and it's in Tampere here. So Tampere, and there's two stations near here, Pirkkala and Tampere. So let's take Siilinkari, and we're going to download the observations related to wind speed. And it's going to be mean wind speed, and this is going to be at 10 meters. So I'm going to download the results to Excel from here. So let's take these ones. There is a little extra, seemingly, it took this year's values as well. Let's not do that now. So deleting those ones. So this is Siilinkari at 10. So actually I could make it in a way. So we're going to put indexes in here. It's just easier to draw. So I'm going to put, let's put this ERA data. So this ERA 5 is in here and Finnish Meteorological Institute, FMI, is this one in here. So we're going to see how well do they correspond to one another. Actually, I can take these ones as well. Oh, it didn't know how to name those. And it seems that my Excel is lagging a bit. Yeah. So this one is the, did I take it correctly? So this ERA is here and Finnish Meteorological Institute is in here. Let's zoom in on a bit. So ERA 5 seems to be higher. That seems to be a bit peculiar. I'm going to just check the coordinates for Tampere. And let's check if I have the same coordinates in here as well. Oh, gonna have to change the name. Or the rather take it from the original file. So let's see if I go backward 61.5, 23.8. 61.5, 23.8. Yeah, that seems to be correct. And this was Siilinкari. Yeah, they seem to be the same. So there shouldn't be any problem with the data. Let's see the Siilinкari. So now that we have the data in here, we can go ahead and plot it. So we can get, assuming we can't, let's only take the other from here. So inserting a scatter chart, yes, and then we're gonna have the other on top of it. So I'm just gonna click from here, Control C, Control V. So now I have two data sets in here, which are pointing to the same values now, but I'm going to change the other one into here. And this blue one is the Finnish Meteorological Institute, and this is the red one is the ERA 1. So let's go ahead and zoom in, for example, to 1200 and 1000. Yeah. So it seems that this Finnish Meteorological Institute data, it fluctuates a bit more and it's seemingly a bit higher all the time. And that was one of the assignments in here to explain why. So compare the data and explain the difference. So the reason for that is that Siilinkari is at uh, sea level or lake level. It's on a lake, so it has a bit more uh, or rather higher wind speed than this average data from this ERA 5. So the ERA 5 average is, I think it was some 28 kilometers, the grid size there. So it averages the data from there. So it's good to know that why this difference occurs and why is there more variation, because this is from one place and this is averaged, aggregated from a larger area. So moving on from that, from the ERA 5 data, scale the 10-meter measurement height wind to 100-meter height. So let's see the power law from here. You can see that the power law has the initial or the original velocity, and then it has the heights, and then it has the exponential coefficient. So actually, we could just say not one per alpha, but I've seen this used that it's alpha, and this alpha varies, or actually, yeah, it's in here. So it's this A. And so it's this Hellman exponent. And for really smooth areas, this Hellman exponent would be 0.1. And for like area with a lot of forest as Tampere, maybe 0.3 or 0.25. So let's try. A equals 0.1. And now we have these wind speeds in here. What I'm going to do is I'm going to plot, or I'm going to modify this rather. So the initial height is 10 meter and the wanted height is 100 meters. So in here, what I'm going to do is I'm going to take the initial speed from here. Actually, it's easier if I just copy and paste. Oh, there seems to be, by the way, some zero values or values with no data in here. So that is something that you can filter out by just changing it to zero with the if statement. But let's take this one, and I'm just going to copy and paste it here so I can delete this one from here. So everything remains the same, but now we have some room in here. So we want to compare this 100-meter data and something that we are going to extrapolate based on this power law from this 10-meter data. So let's calculate the new modeled 100-meter data. So it was the original wind, and then wanted divided with initial height to the power of 0.1. And actually, we could make these just going to put the numbers in here. So I can make these curves like such as load duration curves that you're going to put them into the descending order. So let's put large from here, the array. And this is going to stay constant. And then we're going to put the first largest. So that is the, or rather from this original wind speed and then the modeled wind speed. So this is the original 100 meters. So let's put original 100 meters and model 100 meters. So this is modeled, and again, one in here. So now we have the like wind speed duration curves. I guess you could call it that. So now I'm gonna put it to this original 100 meters, and let's change this one. Well, this would be the same, but either way, let's change it to here. And you can see that it's not the same, but now if we start to play with this exponent, should go, let's see. So this is the, oh, did I put it here? Yeah. Oh, it was it was about not updating the screen. Yeah. So 0.25 maybe. And now you can see it's rather close. So this power law can be, if you only have wind speed data from 10 meters per second, such as in Siilinкari in Tampere measurement station, then you can extrapolate that up to 100 meters or maybe 150 meters, which would correspond to the height of a wind turbine nacelle. So if you don't have the 100-meter wind speed component in here, you can still scale this lower level measurement data if you know this environment, and you can maybe also fit this exponent based on this ERA 5 data. Okay, so moving on from there. So then we're going to download the data from Lestijärvi. So let's change the code in a way that we have Lestijärvi's coordinates in here. So let's ask Lestijärvi longitude and latitude. So this one in here, and then this one in here. And let's put Lestijärvi speed. Lestijärvi speed, and let's extract the files from there. So let's check if the program made the, yeah, there's the Lestijärvi speed. So now we have the speed from Lestijärvi, and the assignment was that calculate the viable parameters for both Lestijärvi and Tampere wind speed at 100. So let's put from this Tampere wind speed, this was the original file, and from here, so I'm going to take Tampere wind speed at 100 from here. So let's put it to Lestijärvi. So this is Lestijärvi, and this is Tampere. And if we want to make the viable fits for these, what we need is the probability densities of these ones. And actually, this would be maybe easier to do in Python, but I'm still going to show it in Excel, so it's kind of easier to see what's happening in here. So let's make a vector from maybe 1 to 0 to 30. And then I'm going to again calculate the probability density of these numbers in between 1 and 0. So this is going to be 0. So in here, we're going to use, as in the earlier exercises, we used this count if data. So we have count, or rather count ifs. So in here, we have the criteria range, this one, and we're going to have to lock this one down. And then what I'm going to do is I'm going to say if it is higher or equal, this is the syntax for it, than 0. And then let's put this one in here. So it's going to be higher than, or rather lower than 1. So it's going to calculate the numbers, how many numbers fall in between that one, and then count how many numbers are in here. So let's see what comes out of it. So you can see that we have these kinds of, let's make a graph with points rather. It's easier to see. So it's rather nice format in here. So from 100 meter, we have that wind speed. So let's make it from, so this was for Lestijärvi, so Lestijärvi, and this is for Tampere. And I'm going to change, this is again 0, and I'm going to change these ones to the numbers and these ones to Tampere. Yes, like that. So we can have the other one as Tampere and other one as Lestijärvi. And for some reason, it seems that the data is really similar. But still, it's not the same data, but we can make the viable analysis based on that. So how to make these or extract the viable parameters? What you need to have is the kind of width parameter, or let's see what it's in Excel. So if I'm going to put viable distribution, it has X, which is the velocity in here, and alpha and beta. So let's put here alpha, beta. So for Lestijärvi, not sure which one is which, but the average speed is going to be something like 6 for these ones, and that would be alpha to be 2 at the beginning. So let's put viable distribution. Viable distribution X equals this one, alpha for Lestijärvi equals this one, beta equals this one. Use the dollars, and it's not going to be cumulative, it's going to be a probability density function. So we're going to see, I'm going to add this one to be here and the other one in here. So these should go in a way that they overlap each other. And this viable distribution, actually, I can make it in a way that it doesn't have these markers, it rather has a line. Oh, no, 1 point selected from there. So now, no markers, just a solid smoothed line. So we'd have to get these points to match the original data that we have. I'm going to scale it from 0 to 20 so it's easier to see. Yeah, so how to do that is, so this is again Lestijärvi viable distribution, and this is Tampere viable distribution. And this is the Tampere parameters. Let's actually put them like this. So alpha and beta are in here. So this is the Lestijärvi case, and Tampere would be a similar. Just put the velocity in here and change the parameters in here. And what we can do is we can calculate the errors. So this one is going to equal Lestijärvi original data minus Lestijärvi Weibull distribution data to the power of 2. So that's the square error of these. So Tampere probability and Tampere Weibull distribution. Yeah. And the sum error. So we're going to take the sum error out of all of these. And I'm guessing that I might have to multiply it with 1,000, for example, to be a bit more exact, have a bit more resolution. And then you can use solver. So I can take data, solver, and if you don't have the solver at site in here, press File, Options, Add-ins, Excel add-ins and go. And from here, you're going to say solver. And the solver is a multi-objective optimization tool. So you can use this one. So we're going to select this one. We're going to minimize it. So we're going to minimize the error. And we're going to use this Lestijärvi data from here. And let's see if it solves it. Yeah. So there's the Lestijärvi parameters. And let's make the same for Tampere. So this is Tampere Weibull distribution, and this is Tampere data. So they seem to be rather similar. So again, data solver, let's solve this one by changing these ones and solve. Yes. So now we have the Weibull parameters for both of those, and they seem to be rather similar. Maybe Tampere has slightly, so this one was for Lestijärvi, so Tampere has slightly less average wind speed in this 100 meter. Okay, so now the final one, calculate the yearly production of the wind farm in Lestijärvi. So this gives us some data for Lestijärvi. So there is 69 wind power plants. They are 240 megawatts high. It's the Siemens Gamesan turbine, and rotor diameter is 170 meters. So let's see. What we need for it is some temperature data. So let's go into here. And Lestijärvi, I guess, is rather close to here. You can check it from the map, but I'm going to take the temperature from there. So rather than having wind speed, I'm going to take air temperature. And you're going to see soon what do we need it for. So this one, and download observations from year 2024. And now we have the air temperature in here. And if I recall right, there was some gaps in between here. So we're going to say if is number, then you're going to give me this one. Otherwise, maybe give the previous value. So if this is number, yeah, so I was missing this one. So you're going to give this one, otherwise give the previous value. So like that. So now we have 2024 temperature data. I'm going to copy and paste it here, and I'm going to make some room for our calculation into here. Like that. If I can change all of these, yeah, like that. So let's take the temperature into here, and then what I want to calculate is rho. So then air density, because I need it for the production equation. So the power of wind turbine is efficiency times 0.5 times surface area of the rotor times air density times V to the power of 3. And again, we might want to scale up this wind. So I'm going to assume that it has the same parameter. So this alpha parameter or A parameter 0.3, the Hellman coefficient would be 0.3. So it's this 100 meters times, now it would be 155. So the nacelle height, if you're looking from here, the maximum height 2040 meters and the rotor diameter is 170 meters. So based on that, the nacelle height is going to be 155 meters. So I would have 155 divided with 100. So that's why I'm going to put 155 to the power of 0.3 and maybe put 0.25 as we had in Tampere. So this would be the wind speed. So wind speed at 155 meters. That's the temperature. And then we need rho. And for rho, so from PV and RT equation, we can say that rho equals mass divided with volume, which equals P molar mass divided with RUT. So we need RU, which is 8.314 joules per mole kelvins. Then we need pressure because the data didn't provide that 0.10300. That's how many pascals. And then molar mass of air 0.028965. I'm guessing that was right. So rho equals pressure times molar mass divided with RU divided with temperature. So this one plus 273.15. That's not right because we need the parentheses in here. Yes. So that's how many kilograms per cubic meters. So let's calculate the power. And actually now what we can do is we can rate the power. So let's have a whiteboard. So since we have the wind speeds and the power law equation is going to go, so the power of the wind turbine as a function of velocity, it's going to go like this. But at, let's say at 3 meters, we're going to start. So this is the cut-in speed. These ones don't produce anything because of the turbine inertia. And then it's going to go up till, let's say, 15 meters. And from 15 meters to 25 meters, it's going to stay flat. And then we're going to cut it out. So cut in, rating, cut out. And the power curve is going to be a bit smoother like that. But we're going to nonetheless use this form. So how we're going to manage that? We're going to ditch all of these values and all of these values and everything after that between 15 and 25. We're going to start rating. So in here, essentially, wind turbine sees 0. In here, it sees 0. And in between here, it sees 15 meters only. And these are the values that we're going to be left with. So let's put cut in, rating, cut out. Cut in is going to be 3. This is going to be 15. This is going to be 25. So let's make some room in here. So first, let's cut out the values from here. So if this one is going to go below 3, then give 0. Otherwise, give this one. And after that, I'm going to ditch all the 25s. So if this one is going to go above 25, then give me 0, otherwise give me this one. And then finally, now if this one is going to be about 15, then give me 15, otherwise give me this, and you have to dollar these ones. So now we have the wind speed that the wind turbine would kind of like see. So let's go ahead and calculate the power. So power is going to be, oh yeah, we're still missing the efficiency. Let's put 0.45. According to Betts law, the maximum number is something like 0.6. So from here, this one times 0.5. Oh yeah, and again, we still need the diameter, which is 170 meters. And based on that, the area is going to be this one divided with 2 to the power of 2 times pi. Well, that's how many cubic meters. Diameter divided by 2 to the power of 2 times pi. Yeah. Okay, now I think we are ready. So this one times 0.5 times area, not that one, times rho, which is fluctuating, and the wind as well in here, to the power of 3. And let's divide that with million, so we'll get megawatts. Yeah. And now we can just have a sum of this one. So sum from here out of all of these, because this is on an hourly basis. And as you can see, there's some extra values, but it gives me 0 in here, so it doesn't matter. So sum and divided with 10 to the power of 6. So we'll get, no, let's see. So this is megawatts. So this would be megawatt hours. Oh, yeah. And one more thing, number of plants was 69. So this is going to be multiplied with 69. Yes. So that's how many terawatt hours we have. And this Lestijärvi page says that it's over 1.3 terawatt hours. So it just so happens that if I were to calculate this power, so this one was power in megawatts, if I were to calculate it with the original wind speed at 100 meters based on the equation like this, then it would give me much closer to 3 terawatt hours. So I'm not sure how they actually did calculate that. There might be that they took into account, for example, the wakes, so the Jensen wake coefficient based calculation for the wind farm kind of positioning. So the wind turbines disturb each other. But based on this calculation, wind speed 100, we're going to scale it up to wind speed 155. We're going to calculate rho based on temperature, and then diameter was given. And then we have the efficiency here and how many power plants. So that's a crude way of estimating the power. So that is all of the exercises at this time.